Why electrons settle into shells and don't fall into the nucleus. In this things, there are many concepts in chemistry, but the most basic is an atomic model. That is 3D engineering as to why things build up like they are. Specifically, the important part of this is the properties, the forces that are involved, the electrostatic and the nucleostatic, also called the nuclear forces. With those, we'll get an understanding of the most fundamental part of building an atomic model of the universe. Now, there are three fundamental forces. The first is radial electrostatic. That is isotropic, which is a fancy name for the same in all directions, and its acceleration or force is 1 over distance squared. Now, this is shown by the red arrow here. So if you have an electron out here, it's pulled by the opposites attract rule and like kind repel. The protons in the nucleus versus the electron are opposite. Minus times plus means it's going to have distance getting smaller, attraction. Now, that is offset by what was discovered as an extra 1 over r force that is also isotropic, but thereby its acceleration is 1 over distance cubed. And the direction is always opposite of the electrostatic. Now, we call that the strong nuclear force. Now, most people know the strong nuclear force as the opposite of electrostatic that keeps a nucleus in place. And that's for every neutron. If you put it between the protons will be separated enough but held together by this force because a neutron has radial nucleostatic but not radial electrostatic. And then the third part is an axial nucleostatic, okay? And that is towards the poles, this green arrow. So while these two are isotropic, the same in every direction, and opposite, this one is towards the news. And that is called weak nuclear and also is sort of the start of magnetism. Because as you get a balance here with this extra 1, you get these starts to think magnetic shapes as that changes depending upon the angle theta. Now let's see how this specifically applies to the electrons staying in a shell, which is mostly the offset of the red electrostatic versus the solid green radial nucleostatic. So for the one proton, one electron equilibrium is at the Bohr radius with the symbol A sub O. So as I said, there's an electrostatic force here in red, and that's going to negative infinity. Now this graph is physics positive, meaning the acceleration is positive away from each other, so getting bigger, hence why positive, and physics negative, getting smaller and coming towards each other. This force says basically that problem, the falling into the nucleus dilemma. However, that 1 over extra r force actually gets bigger faster. That's the funny thing. When you have 1 over distance cubed or 1 over distance squared, that becomes immaterial. The red line here is the difference between the two. And as you go away, 1 over distance cubed becomes immaterial. So that for anybody beyond 1 molecule away, say 10 times away, would be 1 over distance cubed 1,000ths, 0.001. That sort of level is not important to chemistry. But the funny thing is that At the Bohr radius for hydrogen, which is the simple one-to-one interaction, has both forces as exactly the same, but opposite in direction. And more importantly to why they don't fall in, as distance gets smaller, 1 over distance cubed actually gets bigger faster. This black line becomes a wall of repulsion inside the Bohr radius. And obviously, if you have more nucleons, that distance changes based upon the counts in there. But there is a wall, and that is why electrons are not falling into the nucleus, because of this secondary force. So the important things to learn is that thereby it doesn't do it. Now everybody knows this, and this has a specific value. Both the positive and the negative here at this point are both the Planck energy at Bohr. So I call it the Planck at Bohr. This one is positive, pushing it away, and this one is negative, pulling it towards, the net being 0. So the electrons stay. If they get too close, they're pushed away. If they go farther away, that physics negative actually pulls them back. As you can see here, if this is a very magic direction. Through 0, from physics positive to physics negative, is a self-correcting equilibrium. You go further away, it's pulled back. You get closer, that wall of repulsion pushes it back. Now, the second part about understanding electron shells is that there's the Pauli hemisphere logic. Once you know about this wall inside the Bohr radius, you now have a net 2 force. So the electrons want to move in, but this one is negative and negative. Negative times negative is repulsive. So as a result, electrons want to be as far away as possible. That leads to Pauli hemispheres pairs. And that is the basis that these electrons are repulsive to each other, but attracted up to that wall of repulsion at the Bohr, inside the Bohr radius. You see, if that gets out of balance, if the electron is over here instead, it's repulsed from here and it is attracted to the nucleus. Now, the rules of vectors is that you basically just add them together. We translate this vector so it's right at the end of the other one. And so this electron wants to get pushed here all along that circle until it gets back to that 180-degree position. Thank you.